you said you know, that you don't present me, but I still want to thank the organizers, in particular Raoul and Mathilde, for having me here giving this lecture series. It's a bit unfortunate, this after lunch slot, so everybody's digesting the food. It's going to be a bit tough, so I try to keep it as light as possible. Okay, just to introduce myself and the research interest a little bit. So this is going to be on numerical methods for quantum many-body physics. And so just to introduce myself, name is Johannes Schachenmayer. I am a researcher and I'm running a research group at the University of Strasbourg. Strasbourg, if you don't know, it's exactly at the border between France and Germany. It's a beautiful place, as seen from this picture here. And there, the group that is working with me at the moment is quite international. And as you may see here, I have, since a few years, I have quite the Brazil connection with regular students coming to visit me. Some of them even in the audience, like Pedro up there. And so especially I always have this collaboration with UFSCA and the group of Romain Bachelard, who keeps sending students to Strasbourg, which is a great thing. Okay, now to the topic. So I was just want to do a bit of motivational slides, just a motivational talk about what I'm trying to tell you. So the title is hands-on, but I don't just want you to learn how to get results, but I want to kind of do a bit of a bigger motivation, because I really believe doing computations or numerical methods is really also a way to help you understanding quantum mechanics. Just by trying to simulate it, one can really learn something about it. And that's kind of the general theme. And what I'm really interested in is quantum many-body physics, right? So we know that quantum physics works extremely well on the, oops, there's the pointer here. We know it works extremely well on this very small scale. So single atoms, as we have seen here, they're extremely well described by the laws of quantum mechanics. But then if you make the systems bigger and bigger and bigger, then the physics tends to become classical, or well described by classical physics. And it's actually quite rare that one sees some macroscopic quantum effects. Examples are, for example, superfluidity, which you will hear about also later here, or superconductivity. But this is quite rare and happens typically in extreme conditions, very low temperatures. The reason for this is because if I think about quantum many-body physics really as something that happens on a gigantic Hilbert space, then this Hilbert space is really huge, right? So if I have a system of n particles, whatever these particles are, they can be bosons, they can be two-level systems. If I just do many of them together, then this Hilbert space grows exponentially. So it's going to be a gigantic place. But then it turns out for all of the effects that we see, even for these macroscopic ones that I showed before, so even something like superconductivity, it's typically described by mean field-like theories, so it doesn't really make use of this big Hilbert space. So typically the physics only happens in a very small corner of the Hilbert space, and there are many reasons for this. Reasons is, of course, every quantum system is coupled to some environment that destroys the quantum nature. There is some disorder in the system. And also, the interactions are not arbitrary, but usually there's a finite interaction range between particles, usually just contact interactions or very short-range interactions. Okay, and I think at the moment we are living in exciting times, because now there's all these amazing quantum computing or simulation machines being built, which really try to fight these things, right? So what a quantum computer tries to do, with some coherent control, it tries to find ways to really explore this bigger Hilbert space. Right, so imagine you have a quantum computer, then you can do quantum gates, and you can really start exploring what else is out there in the Hilbert space. And this is quite exciting because for several reasons. On the one hand, I find this always quite nice because it's actually not even clear if quantum mechanics will work on this macroscopic scale. So building these quantum computers will tell us if one can make really macroscopic quantum physics. Maybe not, who knows? Nobody has done it. And then, of course, on the application side, there could be exciting things to do, like engineering material properties, making better sensors, or doing better computation. Now, what the approach that in my group we want to do is kind of to approach this many-body problem using classical computers. Right? So fundamentally, what I will talk about here is how to numerically solve the Schrödinger equation or some open system master equation and put it on this classical computer. And there's many motivations for this. On the one hand, it's of course good to model experiments or to really check the status of some quantum advantage of a quantum computer. So far, there's no quantum computer that can do something that the classical computer cannot do. Or, of course, interesting could be to do this to find some new emergent macroscopic quantum phenomena that one could you look at in the future. But the last point I want to really highlight, and this is what this lecture is really about, these 4 lectures, what I really like to try to understand this quantum many-body physics fundamentally from a classical complexity theory. So really trying to rebuild the system on your classical machine, and I think this really helps you to understand something about quantum physics. Okay, so much about the motivational speech. Good, so here's what I just kind of said. So what I want to do here, I want to give you a little tour through some numerical methods for simulating really large-scale quantum many-body physics. And the motto is to really do it from scratch, right? So what I don't want to do is I don't want to use some toolboxes where you say simulate this spin model and then it simulates it, but I want to really build like a Hamiltonian from scratch, a state vector from scratch, and then just do the evolution and introduce a bunch of numerical techniques to do so, which also give you actually quite the physical intuition. And I really try to do this is the first time I tried to do it hands-on. So I want to stop in between and just really show on the computer how to do this. And if you have your own laptop and if you have Julia installed, you can also just follow these examples along. Okay, so these are the topics. So I have 4 lectures. I think I probably have a little bit too much topics, so I would rather go slow and then skip something. In the end, I'm also going to share all of the PDF slides with everything. There's all of the code that you need is written on those slides, so you can just have a look and then implement it yourself. Okay, and the topic is going to be today, it's going to be quite simple, just really some fundamental how to write numbers on computers, and then I want to go to exact diagonalization. I'm sure many of you have heard. Some other have wondered why it's called exact diagonalization. And it's just basically solving dynamics of a quantum system fully exactly without any approximations. Then in the second part, I want to go to a bit of more advanced techniques, in particular sparse matrices, so that you can do bigger systems. Introduce something very nice, which is called Krylov space. And if there's time, talk a little bit about simulating open systems. Then this is still up to here, still exact diagonalization, meaning everything is going to be exact simulations. But then we will relax this and look at approximate simulations. In particular, I will introduce mean field approximations and some methods to integrate mean field dynamics. And then for the final lecture, I thought I'll do something more advanced. So there I don't want to do any tutorial part. I really just want to give you sort of a handbook on how one can go beyond, in particular with so-called matrix product states, which is a super nice technique that allows you to really simulate dynamics of very large systems. Okay, and I have this tutorial part, so I try to do it, I don't know, not quite half-half, but I have always a theory lecture part and then this tutorial style. In particular, I will talk about simulations of spin models and a little bit also about Gross-Petersky equations, which is something you will hear in other lectures from Hélène Perrin, I think. Okay, great. And just to get one thing out of the way, H bar always going to be 1 here. In particular, when you do numerics, this is, of course, very important because computers don't like extremely small numbers, extremely large numbers. Your computer likes the number 1. The number 1 is the best number you can write down in your computer, or 0. Okay, so the idea for today, I have 3 parts. The first part is something very fundamental, just thinking about how to write numbers on your computer memory. And then the second part, I will go to this exact diagonalization, what it really means to diagonalize a Hamiltonian and how to do it on the computer and how you can use this to simulate time dynamics. And then I want to go to something tutorial style, really simulate dynamics of a many-body spin model, something that has been, well, not too long ago, be done really experimentally. So you will see how easy it is to kind of reproduce some experimentally observed dynamics in some cold atom systems. Okay, any questions? So if you have any questions, feel free to interrupt me. As I said, I want to go rather as slow as possible so that I carry you through the digestive phase as good as possible. Okay, so in the beginning, just I want to think a little bit about how do you actually store a number on a computer, because what we want to do is you want to just do calculations, so we want to do stuff with numbers, multiply numbers, add numbers. And there are two types of numbers. They are sort of floating point numbers and integers, right? So integers are just numbers 0, 1, 2, 3, 4, 5, and so on. So now, of course, your computer only essentially knows two things. It knows either the bit can be true or false. Right, for a computer, the memory says current on, current off, means you have 1 or you have 0. It's actually funny to note it's not actually 1 and 0 you have, but it's actually sort of really an information that you store here. Right, so for example, if you think like if you have false and true and you say true plus true, it's not going to be double true. Right, so there's, no, you cannot compute really with kind of information. So you have to do tricks, you have to write down numbers and define them in some certain way. So your computer works with this kind of digital memory. By digital nowadays, it means 0 and 1. But just a fun fact, the word digital comes from the Latin word digitus, which means like the finger, and it just comes from the fact that people started counting with fingers, and that's why you call it digital. So how does one do this on a computer? So I will first start with this example of simple integer numbers. Right, I'm sure you all have kind of seen this before. For example, what I can do is I can store the number 0 here. I can just do with 0, 0, 0, meaning false, 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 false. I use here just a 4-bit example. But first of all, I want to also store not only positive numbers, but also negative numbers. So one of these bits I just call the sign bit. Right? So if I put this to 0, then I say I use a positive number. If I put this to 1, then I say my numbers are negative that follow. So now I have these 3 bits to store some numbers, and I can start, for example, with 0, 0, 1, which would be the number 1. The number 2 would be 0, 1, 0, and so on, and 0, 1, 1. Right? So you do this kind of digital counting with just zeros and ones. The formula for making this conversion is written here. So I give these bits here some names. I call this the bit 0, the bit 1, the bit 2. And then, for example, the number that I have, I will get from d2 times 2 to the power 2, d1 2 to the power 1, and d0 2 to the power 0. Right? So it's really this binary representation of number. I use the base 2 for writing down my numbers here. So now I can think how far I can go. So if I start with 1 here, the maximum number I can have is 1, 1, 1, which in this case would be plus 7. And then if I do the 1 here, then I would have minus 7. But then you actually see that this is not quite the most efficient way of storing your numbers. So then actually in your real computer memory, one does something funny. So because here now I would have sort of the plus 0 and the minus 0, and this is kind of overkill to have 2 zeros. I want to have 1 zeros. So then instead, the convention is that one says this number here is actually minus 8, and then one keeps counting up from minus 7 again. Okay? And this can have some funny consequences, and this is the only reason why I show you this. For example, if you, in your code, we will do this later, if you define a number to be 1, right, then this is, the type of this number is an integer with 64, which means you use 64 bits to write down this number. Right, which means one can actually look at kind of gigantic numbers here. The biggest number would be 2 to the 33 minus 1. And then in your computer, you can try. It's kind of funny. If you take this number here, and if you add 1 to it, you actually switch from this gigantic number to the negative gigantic number. Right? Because you go really from this one, you add 1, you go here. So you go to the most negative number afterwards. So it's just important to keep in mind that there's a certain range of numbers that you can, you dedicate a certain amount of bits, and this gives you the amount of numbers that you can actually write down. And this is, of course, usually more than enough, unless you mess with H-bar. Okay, good. This brings me already to the next important part, because integer numbers are one thing, but the much more crucial numbers are actually floating point numbers. Right, so I want to write something like 1.375. Right, so how this is usually done, so there are several conventions here. I don't want to go too much into the details of this, but fundamentally what you want to do is you want to write sort of any numbers plus minus 1 point some fraction and times 10 to some exponent. Okay, so here one can save a bit of money because one can always keep these fractional numbers, these floating point numbers, normalized in the sense that every number I write is 1 point something, and then I don't need to take care of the 1, where the 1 is always set. So always what I have to only store is all of this fraction here that comes after the 1. And for typical convention, one uses all these bits here to write down the fraction that comes after the f. So in this convention here, 52 bits. This is the one that your computer uses. Almost any commercial computer uses this. But then on top of this, I also have to store again like the sign of my number. So I have again a sign bit, and then I have an exponent here. And the convention here is, as I said here, the fraction is written in this form that I have 1 plus bit f0 is this one here times 2 to the minus 1, f1 times 2 to the minus 2, and so on. And I go all the way up to these 52 bits. And for the exponent, the convention is that one takes the number that is stored here in this integer convention that I had before. So in other words, one uses an integer, but one normalizes it such a way that I subtract 1023, which is 2 to the power 10 minus 1. And then this exponent can be positive or can be negative, depending what one looks at here. So easiest way to just show it with an example here, I flipped a few of bits just for fun. And you can see, for example, if I look at this exponent first, this exponent here, this has a 2 times 1 times 10 to the power 10. It has a 1 times 2 to the power 0. So this is 1024. This is 1. And then I subtract again 1023, which is 10 to the 10 minus 1. So this gives me 2, which means that this number has an exponent of 2. And then the fraction here is written with a 1 here on the f1 and on the f0, no, and the f1 and the f2. And that's it. So I have 2 to the 0. This is the 1 plus this plus this. So I can calculate that this is this number here. Together with the exponent means that this means something like 5.5. Okay, and this is actually a number that the way that I've written it down here, right? This is really 5.5. So this is a number that's exactly represented in your computer memory, can be. But of course, be aware that there are some numbers that you will encounter then at one point which you can only write down approximately. Take, for example, pi. Right? Pi has a just infinite number of fractions after the digit. So you cannot represent pi up to an arbitrary precision unless you start using more bits for representing this. And the reason why I show you this is just important to know where the limitations are. And again, the best possible number I can write down is 1. But 1.0 I can always only write down as 1.0 and then plus minus 2 to the minus 53, because here I only have 52 bits. So the error that I make is always plus minus 2 to the minus 53, which is something like 10 to the 16. Right? So it's always, that's what people mean when they talk about machine precision. People talk about this a lot. If you use this type of thing, which is this so-called double precision, which uses these 64 bits, then you have a relative precision always of 10 to the minus 16. So again, you see definitely if you put like h bar in there, then you have a tiny small number, you have to renormalize this, and then you would get some very high imprecisions if you calculate with these small numbers. So it's much better to normalize the units, ideally setting one energy unit in your Hamiltonian to 1, and then do everything in these simple units. Okay, and this is all of what I wanted to say about numbers, really. Okay, but now to quantum mechanics. Right, so quantum mechanics, how do you describe your system? Right, you have something like this here. It has two elements. It's like a state vector if you have a closed quantum system. Right, so a state vector, you have to, in general, for any quantum system, write it as a vector with some complex numbers here. So if I have a Hilbert space size of capital D, right, this is really a vector with D elements, or if you like, a D times 1 matrix, different way of thinking about it. And in general, if my Hilbert space is dimension D, then I have to take care that in general, these are complex numbers. Right? So I need to store the real part, and I have to store the imaginary part. So which means I need two double precision numbers if I want to do double precision. So it's then 128 bits, which is 16 bytes. So this is the memory that I need to just write down a vector for a Hilbert space size of D. Okay, and then I have things like Hamiltonians or quantum gates or some observables or a time evolution operator. And then these are going to be in general D times D matrices, right? So then I have to store like for every combination of ij, for example, I have to store a number here. So this is a gigantic matrix in general. But we will see, and as I mentioned before, most of nature doesn't really make use of this whole just gigantic couplings. That's why usually relatively sparse matrices one can get away with. We will see this later. Okay, but I also want to define this concept of a state vector not only for quantum systems, but really also for a very general system. Later you will see something like the Gross-Peteevsky equation. The Gross-Peteevsky equation describes something which is called the condensate field, which is not technically really a state vector, so it's something else, because then you can have nonlinear equations. So fundamentally, I just want to define a state vector as any set of numbers that allows you to describe your system. Right? But then how the system evolves depends on the equations. And in general, I can have just an ordinary differential equation, meaning that the time derivative of the state vector is going to depend on some function, which can depend on the time, and it can also depend on the state vector itself. Right? This is typically what happens in classical physics. You get nonlinear equations, meaning that at every point in time, kind of your Hamiltonian changes. So your function on the right-hand side of the equation can depend on the state itself. We will also see this later, in particular, if one makes these mean field approximations. And the Schrödinger equation, sort of, it's just a linear equation. It's just like a subclass of this type of equations, because here my function on the right-hand side is just simply a Hamiltonian, a matrix multiplied with a vector, so it's a linear equation. But again, a state vector can really anything. If I deal with open systems, I can define a state vector as all of the elements of my density matrix. Right? I can write this matrix, think about it as a snake, then it's also a state vector. Or take, if you like, a system of two classical particles, both have a position and a momentum, then I can write this as a vector with these four real numbers, position, momentum, position, momentum. So this is a really general concept. All right, so then just to, first of all, I said the first two lectures I want to stay really with fully exact simulation techniques. And then one can ask, of course, how far can I go with this at best? And so I will, in particular, almost all of the part of the first two lectures, I will stay with a bunch of two-level systems. So think about really these two-level atoms. You can also call them qubits, if you like. You can call them spins, spin up, spin down. And I will only talk about the spin models and then have a set of these spin models. Now, of course, if I have this, then if I have n of these spins, then my Hilbert space will be 2 to the power of n. So here I was then plotting this memory requirement. I could use single precision if I don't want to have the precision that I showed you before. But in general, one should use double precision because there's anyway just a factor of 2 difference between those two. And here now I just plot how much memory you would need as a number of these two-level systems that I add to my system. And then you can think about your computer. I guess it has a few gigabytes of memory, maybe 10. Maybe if you go to some cluster, you can get machines with whatever, 100 gigabytes. But then sort of, if I set the line at sort of 10 gigabytes up here, then I see fundamentally, I will just, this is a log scale, of course. Fundamentally, I will never be able to do much more than 30 of these qubits on your memory, simply because your state vector is too big to write down. Which I want to make two important comments. Actually start with the second one. Of course, if your state vector is too big, it does not mean that you cannot simulate this dynamics, right? Because a state vector has a lot of information in it, and maybe you just want to look at some dynamics of some observable, which is actually quite simple, so you don't need all of this information at all. So this is really just the worst case limit if you really want to simulate everything exactly, and if you want to evaluate all of the correlation functions in your system. The second example, of course, here you may say, okay, but the Hamiltonian actually goes with d squared, so this is really just the Hilbert space dimension, but I want to write down matrices. The cool thing is I want to show you, especially in the second part with this Krylov space dimension, that actually you can even get away with only memory that goes really linear in this Hilbert space dimension. And the reason is because Hamiltonians are really sparse matrices, because you only have usually two-body terms. You don't have like gigantic n-body terms in them. And that's why these Hamiltonians are very sparse. And the number of non-zero elements in a matrix actually only scales as d for really all physical Hamiltonians that you want to look at. Okay, good. This concludes the part one. So this was really just some general, it's always good before starting hacking something in the computer, to think about the fundamental limitations and to gain a bit of understanding about what you really want to do. So now in the second part, I want to now really introduce this concept of exact diagonalization. And then afterwards going into using that for simulate the dynamics of this spin model. Okay? Great, so exact diagonalization, as the name suggests, you do a diagonalization of a Hamiltonian. And here I just want to really show what this means. And I want to show you why this helps you to really solve anything in your system, really any dynamics that you want. Right, so you know that if you want to compute an equilibrium state at 0 temperatures, the ground state of the system, you know that you get the eigenvector with the lowest energy, this will be your ground state. But if you do this full diagonalization, if you do compute all of the eigenstates of your system, you can then do an arbitrary time evolution of your system. So this is what I want to show here. So taking a step back, so what's diagonalization? So we want to diagonalize something which is a Hamiltonian, which we know is a Hermitian matrix, meaning that h dagger h is the same as h. And in general, this is a d by d matrix, and just because I have the symmetry property, I know that this matrix is going to have real eigenvalues. Right? So what I know is that there must be a matrix, which is a unitary matrix. Right? A diagonalization is a unitary transformation, just as a time evolution. So unitary is just a basis change, if you like. So I know that there exists some matrix V, which is unitary, meaning that V dagger V is the same as V dagger, and it's an identity. Right? Which means that V dagger is the inverse of V, and the other way around. That's the definition of a unitary matrix. And the diagonalization says that such a matrix exists, such that I can apply it to my Hamiltonian. From the left side, I apply V dagger. From the right side, I multiply V. And then this brings this Hamiltonian in a form which I call E here, which is a diagonal matrix. Right? So it has zeros everywhere. Only on the diagonal, there are non-zero elements. Right? And one can write down this transformation now in different forms. Because I have this unitary property, I can, for example, apply V to this equation from the left-hand side. Right? If I apply V here, then I have V dagger V is the identity, so I have nothing here left anymore. And I apply it on the other right side. I also apply the V, so I can write the equation in this form here, which is maybe more familiar to you because this is really how you think about Hamiltonian applied to some vector gives a number times the vector. And this is what I want to show here schematically. So this is here really just a schematic representation of this blue equation. Right, so I have, on the left-hand side, I have a matrix multiplication of two matrices. Right, so all of these are matrices. So I multiply them according to the matrix multiplication. So I'd go like this for each of the elements. And then if I write it like this, sort of this matrix multiplication here, I have explicitly written it down in an explicit form here. Right, so if I perform this matrix multiplication, it means that I have a matrix here which has an index I and an index j. The one tells me what row I'm in, the other one tells me what column I'm in. The same here, I have this row index and then I have the column index. And the matrix multiplication says that I multiply over one index which is common to the two, so I multiply the column index of the first matrix with the row index of the second index. So this is really the matrix multiplication. And now if I do this math here, then I can see that the chase column of this matrix here. So I take a column, the column number j. If I define this j column here as okay, this is a matrix, but I just define it as a vector where the index of the vector is given by I. Right, then from this simple equation here, I see that from the fact that here on the right-hand side I have a diagonal matrix. Right, so diagonal matrix means that this matrix Eij, the elements of it are related with this Kronecker delta here with just Ej. The right-hand side of this equation multiplies, so it becomes very simple, it becomes Ej v Ij, and now if I define this eigenvector here, I see that this is really now a matrix vector multiplication with Ej being my eigenvalue of this vector. Right, so this is more the form. If I define this really as the eigenket, I define the column here, then I know that my Hamiltonian applied to this vector is just the eigenenergy of this times the vector. Right? So all I want to show is that you see from this equation that really all the columns of this matrix V that you get, they are really all the eigenvectors of your system. And the diagonal matrix here has sort of the real valued eigenvalues in it. Okay, and the same is true on the other hand. If I would take the rows of this matrix V, then they would kind of be the eigenbras of this equation from the other side, which I would just see from this equation if I dagger this equation one time. Okay, so this is just the goal of a diagonalization is really to find this matrix V, and your numerical routine in your Julia or in your C++ library or whatever you want to use, it's going to give you this matrix V if you do a full diagonalization. And then with this, you know everything. Why do you know everything? I think this is better seen from this last part of this problem, right? So if I write the diagonalization as this equation over here, I can get it, for example, now from applying the dagger from the right-hand side. Then I see that this is really, diagonalization means that I have kind of a spectral decomposition of my Hamiltonian. Right, so now having introduced the things I just said before, I defined these eigenvalues really as the columns of your matrices, and these are the rows of the matrices. Then I see that this last form of the equation just is the spectral decomposition, which means that sort of my matrices V just give me a way of writing the Hamiltonian in really the diagonal basis of the eigenstates. Right, means I can write this really as sum over k, ek, and then just projection on these eigenstates. Right, and from this equation, I can see actually much more cleanly now that I can really do any time evolution with this. And this is because of this equation, what I'm going to show here. Right, so if I want to solve the Schrödinger equation, right, I can always kind of formally solve it if you like, because it's a trivial linear equation. So if I formally integrate the Schrödinger equation, for now assuming a time-independent Hamiltonian, everything now here is time-independent, then my state at time t is going to be given by the matrix exponential minus it times the Hamiltonian applied to the initial state. Okay, so this is give you, if I have your vector at time t0, then this matrix exponential here is going to give you multiplied to this vector the state at time t. Now, of course, this is a tricky thing to compute here, the matrix exponential, right? So this is not just taking the exponents of each of the elements of the matrix. It's much more complicated. It's actually just defined, for example, by the Taylor expansion of the Hamiltonian. So e to the minus IHT I should write as this full Taylor expansion, 0 to infinity, matrix to the power of n, and take in general all of these terms in the sum. Later we see we don't need all of the terms often, but here I just write it as this. And then I see now here I can insert this spectral decomposition of my Hamiltonian. That's what I do in here. And now I can use the property that the eigenvectors that I computed, so these columns and rows of this matrix, they're going to be orthogonal. Simply because this V is a unitary matrix. So this, if I take a column and a row and multiply this, it's going to be a Kronecker delta. Which means that if I take any of these things to the power of n, it's going to be again the project on the eigenstate. So because the eigenstates are orthogonal, if I project like n times on the same eigenstate, I can only project it once because the first projection is already enough. Right, so that's why I can now drastically simplify this and just bring these states here back from the exponent back down. And the dynamics, really what dynamics means, time evolution dynamics is really just I take an initial state here, I compute the overlap of this initial state with all of the eigenvectors in my systems that I have. Then I just add this time-dependent phase to that state. Right? So time evolution means just adding phases to these eigenstates. And then this gives me the probability to be in that eigenstate after the probability amplitude to be in that eigenstate after the time. And this is how time evolution works. You just go into eigenstates and then you evolve with a phase. Okay, good. So now this is almost the last slide I want to show before really doing some more hands-off stuff. So here I will not do some hands-off things, But just to show you how simple this is now to do this exact diagonalization, and sort of, I will introduce more of this notation in Julia a little bit later in this next part. But I can, for example, just test how this this diagonalization works. So I can, for example, just for fun test these equations here. So what I can do is I can define a random Hamiltonian. This is a function that is just creates really a number, it creates a matrix, 100 times 100 matrix. I want to make this matrix a complex matrix. So it is really complex real and imaginary parts. And then I just make it a Hermitian matrix just by multiplying it with its own daggered version. In Julia, you will see we just do the dagger only with the little apostrophe here. So this means you add to a Hamiltonian a daggered part, so then this is an Hermitian matrix. And then I can just use, in Julia, one uses some linear algebra. For example, diagonalization is given by this function, which gives me back two things. It's going to give me this E, which is a diagonal matrix. So here this will just be returned as a vector of eigenvalues. And it gives me this matrix V, which is the thing I really want. Right, so. And then I can just check these equations. For example, taking the second equation, I can do H times V, right? So this is in Julia, it's really easy to do this linear algebra things. That's why I'm using it here. So H times V is just really already doing a matrix multiplication of these two matrices. I can subtract now the second part of this, and then I look at the norm of this matrix that comes out, and I see this is a matrix which is norm 0 because it has all zeros in it. But it's not 0, of course. You see what you will get if you do this, you get something like 10 to the minus 13. Right? But now you see, of course, the machine precision, ultimately, I could get something 10 to the minus 16. And the reason why this is not 16 is just because, of course, this diagonalization routine also has some numerical noise in it. Right? It does a lot of operations. It's not up to full machine precision, apparently. So now if we do this type of checks here of this equation, or here these other equations, we see that, okay, we do some complicated things with a lot of numbers, so there's some rounding errors. And this is the precision. So now this, for me, should be 0 in terms of the elements of these matrices that I look at. Okay, now if I want to do some time evolution, as we will do now in this second part, right, I could do two things. I can just do really literally what I just wrote here. Right, this would be just whatever, 7 lines of code to do a time evolution of your state vector. So here I just introduce an initial state vector. These first 2 lines are defining a state vector. So I just take like a vector, a complex vector, which has like a column vector, which is all 0 elements. And then I set the first element to 1, right, just for fun. So it has to be a normalized vector, of course. So I can just set first element to 1. And then I want to know what is the state psi at times t. I say this is another one. I start with an all 0 vector. And then I can compute this vector at times t just by writing sort of this loop over all of the eigenstates that I have. And I do literally what I just write down in this equation here. Right, so first I just compute the overlap of the k eigenvalue here, which is the column of this matrix. This is a very important notation in Julia. It's very similar to what has been done in MATLAB, for example. So if you do something like this on a matrix, so this V is a matrix, this double dot just gives me really a column of this matrix. We will do all of this in a second. Then I compute really the Hermitian conjugate of this. So this is the EK part here. And I multiply it to this initial state. This gives me this overlap, this blue thing here, which is a number. And then to this number, I multiply like a time-dependent phase. Here, this is for time t. So I just multiply this phase factor here. It's another complex number. And then I just pointwise multiply it to each element of the eigenvector ek, and I just add all of these contributions up. This is the sum. And that way, if I do it with this way in this loop, I just keep adding all of the contributions from all of the eigenvectors that I have, multiply it with the corresponding phase, and then I'm going to get the vector at times t. That's one way of doing it, or one just uses alternatively just the matrix exponential function. Right? So this is doing all of that for you kind of in the background. So here, if I use just something like I define a u, which is the exponential of the Hamiltonian with my negatory imaginary part times t. If I do this, and then I apply this matrix, this is the time evolution operator. If I apply this evolution operator to my initial state, I get my output state. And then this happens in the background. And of course, depending on what language you use, one has to be very careful. As I said, sometimes you have to be sure that this is really the matrix exponential that's computed. For example, if one goes back to MATLAB, then this would not be, this would be an element-wise exponential. But you really want to use the matrix exponential here. Okay, good. So this is fundamentally just what exact diagonalization is. And now what I would want to do is I would spend really kind of the second half just doing something with it. Do you have any questions coming up to here so far? Sorry, yeah. Yes, then this does not work anymore. No, then of course, we will come back to this later. Well, one can do two things, right? It depends. If the time dependence is very slow, I can just chunk up my dynamics in little tiny steps. But then, of course, I make and have to be careful about the error that I make from this truncation there. We'll see a little bit about Trotter decompositions later, how to overcome this a bit. But then also one could also use just some general ODE solvers, which is part of the lecture 3 that I can use. So that's when your right-hand side. So what I'm talking about here is really time-independent Hamiltonian dynamics for now. Okay, good. And actually, now coming to this last part, so this is the problem that I want to solve here. So even if you have time-independent Hamiltonians, they're actually quite interesting things to look at. And the stuff that I want to look at here and the results I want to get today, and I hope I can show you that one can reproduce stuff from papers in 45 minutes. What I want to do is sort of something that has been popular maybe something like 10 years ago, where people looked at what you call a quench dynamics in the system. So there was the idea that one takes sort of a many-body spin model. So a spin model is really exactly what I said before. I have a bunch of two-level systems. And then imagine I start with some state, which is a highly non-equilibrium state. And then I really look at the time dynamics of these states. This has been done in many different setups by now. Here, the plots that I showed, they came from the trapped ion community. So what they did there is they did these effective spin model realizations using ion states. So you trap ions in a one-dimensional ion crystal. And then what people have done is that you can use two internal states of the ions as an effective spin representation. And one can engineer an interaction between those spins over the vibrations of this crystal. So one can effectively engineer Hamiltonians like I have them written down here. Forget about this one. Actually, today I only want to talk about that one, which is called the transverse easing model. So here I have a Hamiltonian, which has a pairwise interaction. And the interaction is a sigma z type interaction, and sigma z is the Pauli matrix. I will define it in a second. So this is, if the one spin up, but the other one is spin up, then this is the interacting part. And then on top of this one has a transverse field, which is just a field which is constant, which goes along the x direction. And then what they did in this experiment here, for example, they prepare an initial state. So this is for 7 ions here, right? They have 7 ions, and then one of the spins initially they flip. And now this state is clearly not an eigenstate of that Hamiltonian. It actually has a very high energy. So now all the spins, they're going to evolve as a function of time. And here what this plot shows, it just really shows the expectation value of sigma z. So in the beginning, it's really -1, -1, -1, +1, -1, -1. This is at time 0. And then this information of this spin keeps kind of spreading out to the other spins because this Hamiltonian is engineered in this type of system. And this may look quite simple, but it's actually, there's some physics which is really hard to understand, even up to date, because that's actually a quite complicated Hamiltonian. It's really non-integrable. And on top of this, it has long-range couplings. Right, a specific feature what they had in this experiment is they had this coupling matrix between the spins. It is not only between nearest neighbors, but it can be between spins which is far from each other. And then the physics actually gets very recent and still relatively little understood. And I will show some examples of this later. Okay, great. So, but now I want to go really hands-on, and I want to do this here. I want to do the simulations of this Hamiltonian as I have just introduced it. And I will only use this linear algebra packages, like I will use a matrix exponential function. But all of the rest of the system, I want to convince you, is actually super easy to just construct it yourself by hand without using any toolboxes or anything. And for that, just as 2 preparation slides, what I really base all of my Hamiltonian construction on is given by the following. So first, here I have kind of the outline of what I want to do. I want to do 4 steps. First, I really want to construct these spin operators that show up in the Hamiltonian. Then from there, I will construct the actual Hamiltonian. And then we just simulate the dynamics for this. And finally, we just want to plot some observable dynamics. In particular, the goal is to reproduce this plot here. And this is only 7 spins, so this should be easily doable with this laptop here. Okay, but just as a preliminary, what we need to understand is that, okay, what does it actually mean when we write down a Hamiltonian like this? Because we are on this gigantic Hilbert space, right? Our state vectors grow exponentially 2 to the power of number of spins that I have. And actually, if I write down a Hamiltonian like this, sort of the notation is quite a bit sloppy in a way. Right? Because if I write sum over I, sigma x, like a simple Pauli X matrix, right? So the Pauli X matrix is defined here, just 1 on the off diagonals. Then if I write down like this, it's actually an operator that acts on a Hilbert space of all of the n spins in your system. Right? So what we actually mean by writing this in a more proper mathematical way of writing down things would be that I have an identity acting on the first spin, identity acting on the other spin, so nothing happens. And then on the spin I, the sigma x acts. And again, on the other spins, nothing happens. Right? And that would actually be linear algebra, the real full matrix. Right? So I have this tensor product between them, which is also known as the Kronecker product. Right? So this is the tensor product structure of the Hilbert space, of a composite Hilbert space. Okay, so what I need to do is I have to find the big matrix. I have the little matrix here, but I have to find the big matrix that does this. The same for the spin-spin interaction part. Right now I have a sigma z matrix, which I define here. Note I define it a bit different. The -1 is up here, and the 1 is there. You will see in a second why. And then all of the other spins have identities, and only the spin number I and the spin number j have a sigma z. Right? And that would be the mathematical thing that should show up in the sum of the Hamiltonian, telling me how does spin I interact with the spin j in the system. So what we're going to do is we're going to construct first these type of spin operators using just really this Kronecker function. Right? And what we need is really sigma z, we need sigma x, but actually even more simpler, one can reduce everything to just the spin lowering operator. Right? If I define a spin lowering operator, so I define what my spin down is and my spin up is. The convention I will use is this one here. This should be my spin down, which is the state 1, 0, which is actually equivalent to this one, the ground state, if you like. This would be 1, 0, then this would be the spin down, and the spin up is the, 0, 1. Not only on the blackboard you make mistakes. Okay. Good, then if I use this convention, then if I act with my sigma minus on the spin up, which is wrong here, it will take me to the spin down. Right, and then I have sigma minus, I know what sigma plus is. I can do sort of the many-body operator, just defining it with a gigantic identity on the left-hand side, a gigantic identity on the right-hand side. In between, I define my sigma minus. And then the sigma plus will just be the sigma minus dagger. I can just dagger this matrix, it will be the sigma plus. And then my sigma x is just sigma minus plus, sigma plus, and the sigma z is sigma plus, sigma minus, minus, sigma plus. Right? Okay, and I will use this to really just write this down now. And I think I have to sit down now to be more on the computer level. Okay, so let me show how to lead you through that forest. Okay, so fundamentally, okay, many people nowadays, they use some notebooks. I'm a bit old school. So what I like more is I like to write sort of scripts that do things. I like this better because it's easier if you do really hardcore numerical physics. You sooner or later end up putting your scripts on some cluster, and it's like much better to already think in this way, I think. So what I'm going to do is I'm going to show you here, like this is code just written in a file. It's a simple file. I called it transverse easing model simulation. Right, so far this file doesn't do much. It just, in Julia, you just tell them that it should use some packages. What I want to use is I want to use clearly the linear algebra. And then the other two packages here just for cosmetics. I want to make plots with nice labels. So I used this plot package and this latex string. And then all I did so far, I didn't do anything really. I just wrote a function which doesn't do anything. All of this function does, it just writes the hello world and then returns nothing. Right? So this is always how you start coding in a language. You show it how to write hello world. Okay, so that's the one thing. And then here I have the thing where I will execute this type of script. So just please tell me, is the font size big enough so that you can see? If not, I have a problem, let me know. Right, so the first thing we do, we start test Julia here. Of course, it's already outdated because they update it all the time. Okay, and then, okay, what I can just do is I can just write, for example, I use this include command, and I want to use this script, which I called TI model simulation. Right, and so far, it in the beginning always takes a little bit of time. There's a little aspect about Julia which I like very well because it's actually like a scripted language, but it's still, when you run it, it still compiles your code in time. Right, so it still has sort of the speed of a compiled language, but works also just as a script. If you don't know what this means, don't worry about it. You don't have to know anything about that. But sometimes when you run things the first time, they can take you a little bit because in the back it compiles something, and then when the execution happens, it's fast. So at the moment, it doesn't do anything. I just defined one function which doesn't do anything. It just says hello world here. Okay, so now what I want to do is I want to start really defining this. It was the spin lowering operator. Right, so what I really want to do is I want to define something, let's call it sigma minus, and I had defined it like this. Oops, sorry. So this is notation here, means this is just defining a 2x2 matrix. Up, what happened? Already messing up. I'm going to make a lot of those mistakes. All right, so this is defining a 2x2 matrix, just as I did it before. It's just this semicolon here. It just tells you to go to the next row, really. Okay, and the first thing I should do is I should really check, does it what I want to do? Right, so I said, just to double check my definition of the spin. So this was, this 1, 0 is now the vector, which is the 1, 0 vector. And what I wanted it to be, I wanted this to be the down spin state. So sigma minus acting on a down state should just give 0. Right, so there's nothing below spin down. On the other hand, if I act with this on the spin 1 state, it's going to be this, right? So here's now I had the 0, 1. Wait, I can also write it better. Right, if I write something like this gives me the up state. But then if I act with sigma minus on this up state, it just flips it into the down state. Right, simple matrix multiplication. Anyway, when you write code, there are so many things where you can make little mistakes, so it's always good to check every little step. Okay, so we defined the sigma minus operator, and we know what it's really doing. So we can just go ahead and just now from this operator really make many-body operators. Right, and the way that I want to do this, I want to use it just really using this Kronecker function. And we can do this just live to check, say if I define something which is an identity. Let's say I define now my matrix to explain some notation here. Right? So if I write this thing here, this defines a matrix which is called identity, which is an identity matrix. That's just how you do it in Julia. This 1 is always for the one element mathematically, and then you turn this into a matrix. And this would be an identity. And what I want now, if I want to have, for example, my lowering operator acting for the spin 2, right? I would use the Kronecker delta, Kronecker product function, which in Julia is just called cron, quite easy. And I would do something like an identity acting on my first spin, sigma minus on the second spin, and then I would get something like this, which is now the many-body matrix that you want for your 2 spins, which is going to lower really the second spin only. Right? I can check now, for example, what this matrix, if I define it like this, would do. So for example, if I take, now I have a 4-dimensional Hilbert space. So let's say I start with this vector here. In my convention, this should be the all-down state, right? Because now I start counting. The first element would be down, down. Then the next one would be down, up. The next one would be up, down. And the last one would be up, up. Right? So if I do this, then I see, again, it gives me the 0 element. But on the other hand, if I start with a fully excited state, which would be this state here, this would just lower the first of the 2 spins. And I see I go from here to here. Right? Now I know that the third element of my vector is going to be down, up. Right? So the ordering here actually goes down, down, up, up, and then up, up. It's actually the other way that I introduced it, which is just because of how the Kronecker product is defined here. Okay? And this is the whole concept one really needs to fully construct now, really this set of spin lowering operators that gives you everything that you need. Okay, so that's what I want to do is I want to go here and I want to define a function. Oh, this is really difficult to look here. Okay, I want to define, let me see if I actually should change that. Okay. Now the question is where this thing went. It went here. Okay, let's stay here. Up. Okay, so what you want to do is you want to really just define a function that what you can want to call, for example, build lowering operators. Right? Let's say I want to do this function, and what do I want to give this function? Well, let's give it the spin lowering operator as an argument, because, for example, I wanted to maybe at one point you want to redefine what your spin down means. So you can do this just by redefining what your spin lowering operator means. And then the second thing I want to do is I want to tell how many qubits I want to use this thing on, how many spins. Okay, and now I want to, this is the function. This is going to return something, let's see. And now what I want to do is I really want to go through all of the spins that I have. Right, so I want to write this loop again. Right, so this is a loop that you say, okay, now this is just going through, and this I is really an integer number that's going to increase for every time in this loop. Right, I think everybody has at least heard the concept of this. This is something that I need as a foundation, really. Okay, now what we want to do is we want to really have this big matrix where for my local little spin I, this index I is my, here call it II. This is the index of the spin I want to create this operator on. And I want to sort of have a Kronecker product where on the left side of the spin I have an identity, and on the right side I also have an identity of the proper dimension. Right, so the easiest way to do it, so let's just define what this dimension is. So I have a dimension on the left side. So what would the dimension be? This would be 2 to the power of something. So think about it, for example, this one starts at 1, right? So my first spin is labeled by 1. Then I know that the dimension on the left side is going to be 0, right? So this must be, well, it should be not be 0, it should be 2 to the power 0, it should be 1. So this must be 2 to the power minus II minus 1. Right? And this should be the Hilbert space dimension of everything that's left to my spin at index I. On the other hand, then I should do the one over the right-hand side. It should be something like 2, again, exponentially growing. And now, how many spins do I have right of my spins? So here I have really 0 spins left of my spin, and I have n minus 1s to the right side of my spin. Right, so this should be n minus ii. Right, because if I start at 1, it should be 9. If I choose 10 spins, then it should be 9, so it should be n minus 1 for the first one. Okay, so these are the sizes of my Hilbert space, left and right. Okay, and now all I have to do is I can define something like a left identity, which is just, again, this matrix, which is this identity, and now instead of 2 times 2, it's L left dimension times left dimension. The same on the right-hand side. This is going to be the right-hand dimension. And now I know that my spin operator should be something like left identity. Then there should be the lowering operator, and then I should have the right identity. Okay? So literally what I'm doing here, I'm doing just this. Right? 2 to the I minus 1, left dimension, identity matrix. Right side, 2 to the right-hand side dimension. In the middle, I just do my lowering operator. Okay, and that's going to give me, for all of the i's, after the other, this will be this big matrix that I need. And in principle, it's the only matrix that I really need. Right, because I can fully construct my Hamiltonian from this one single matrix. Okay, so let's just do this. So we have to get this somehow back. So what I do here is I do something that is Julia-like. So I define a vector. And this is a vector of something I don't specify yet, but it's actually going to be a vector of matrices. Right? Because here I produce n of these big matrices, and this is a function that makes n of these matrices. So I want to get n of these elements back, and what I just do here, I use this so-called push function, which to this quantity here just adds an element to this vector, but each element is a matrix. Right? So this is just a data structure that now has all of the lowering operators in it. And that's what I want to return from this function. Okay? Okay, let's see if this works. Good, so what I want to do is I want to now use this function that I just defined. I should include my script again, because this is all, of course, true if I do this. Okay, now I have this function build lowering operators, and I had my sigma m as m defined before, and say I want to do it for 2. I should get now this thing, which is a 2-element vector, which has each element is a matrix. Right, so here what this function does, it creates a vector of these matrices, and the first matrix should be my spin lowering operator as I defined it before, and the second one would look something like this. Right, so this is super nice. So you see there is some structure in creating these matrices. Of course, at this point, it would be computationally much more efficient to just understand the structure of these matrices and just make the matrices by hand. But then there are so much chances for making a mistake or anything. So instead, I chose the way of the physically inspired way of constructing this matrix. And now I can really generalize this to an arbitrary large thing. So for 10 spins now, I get 1024 times 1024 matrices, which are almost 0 everywhere. Right, so you see already that what I'm doing here is kind of really inefficient, because I'm just storing a lot of zeros, which I wouldn't need to store. But we're going to get back to this part later. Okay. Everything good so far, except for the ones that are sleeping already. Good, don't worry. Okay, good. So as I said, now I have a spin lowering operator. But what I really want, I want like the other. I mean, I want the sigma x operators, and I want the sigma z operators. Now, there's one way of doing this. As I said, I can construct really anything from this. So let's define a function which I now call build my spin operators. Let us see what it is here. Yes, okay, and wait, I better just one other one. Okay, good. And now I could be really, really lazy if I would be. So now, instead of having this vector of just the lowering operators, I want to have a function that creates my sigma x operators and that creates my sigma z operators. Right, and to be extremely lazy, I just write this now again in the same way. Oh, sorry. And the easiest thing to do would just to create directly this sigma x operator, for example, now SSM dagger plus SM. Right, and the sigma z operator was something like SM times this minus the other way around. Okay. And I just return both of this. Okay, and this would be a function now that creates all of the spin operators that I then in the next step need to construct my Hamiltonian. Let me see again if this just works. I have to include this again. Right, I have to every time include because I'm defining new functions, new objects in there. Sorry, I did something stupid here. I wanted to give it this vector of the SM operators. That's what I wanted to do. Right, so I just take the lowering operator for spin I, and I construct the thing. It's really good to do this live, then you see all the mistakes that you make. Okay, so include it again. And now I have this function that should work. So I defined my spin lowering operators. Yes. Thank you. Thank you for paying attention. Okay. Okay, I have this vector of these lowering operators, and I have my new function, which builds these spin operators using this vector, and I don't even need to define n, right? Because I get it automatically if I just give it this vector, because I know that the length of this vector is n. I don't know, why not? Okay, and now I can just try to work this function. So now I have a function which should give me the vector of x Pauli matrices, big ones, and vector of z Pauli matrices. And it takes, as I said, the first time it always takes long, and I get something back. Wait, let me first maybe, let's do it for n equals 2 first, because it's nice to understand things. And now, okay, now I have sigma x operator for spin 1. This one makes sense. 1 and 2, this is for two ones, and I have my SZ, for example, which should be diagonal one. This is maybe beautiful to understand, because now you have the SZ operator, so now you would have spin up would be +1. Okay, something about the ordering I don't quite understand. Okay, why not? And x2, what this one makes also sense. Okay, anyway, so I just want to show you now this way, right? I can now really make this big SX operators. Anyway, I will not use this function. I will see in a second. Okay, let's go back to the bigger system. So if I do for 10 this whole thing, and then I construct this. Was it here? I construct these spin operators. I know it's already a bit right? It takes quite a while. Right, so I don't really like that too much. In Julia's, one thing that's kind of useful, one can always, before a command, one can put this add time command, and then this will tell you exactly how many resources this function uses that you use. And you see this takes like 3 seconds, it just allocates, needs this type of memory. And this is kind of, it's called the garbage collection time. This is kind of memory management related stuff. So anyway, so this is quite long actually, I think, right? Because in the end, if you think about it, if you look at this function, what I'm doing here is I really, I take all of these big matrices, and now I take a big matrix here, I do a Hermitian conjugate of this big matrix, and then I add another big matrix. Or even worse here I do a big matrix, multiply it with another big matrix, and then I subtract another one. Right, so this is quite a lot. Right, so now it multiplies these big matrices, and I can actually see that this is really not the ideal way of doing it, right? Because I can, in the end, so let me call this bad function. Right, so in the end, what I could of course also do, I could just do the same function that I had here, and instead of doing this type of addition and multiplication with the big matrices, right, it would be much better if I just do it on the small matrices. Right, so if I here instead of doing it as I did here, if I instead of here, when I construct my sigma x matrix, for example, if I instead of doing this with the small lowering operator here, I can just do SM thing here. Right, and this should be much, much faster because now the actual arithmetic that I'm doing happens on the level of the small matrices instead of the big matrices. Right, so actually, let's try this. Let me now define everything as I did it before. Right, so now it just first does the arithmetic and then it does this Kronecker function. And what I want to show you is that this should be much faster. Build, now let's call this build spin ops. Right, so now I have two functions, sort of the bad one and the good one. This is classic. Okay, I do the same thing here, and now I have the one was with the spin model was bad. Yes, this is the one that takes 3 seconds. Nobody has time to wait for that. Instead, we do the good one, where I now had this SM, and I just do it for 10, and now it takes only 0.2 seconds. And it needs less memory, and this was only the first run. If I run the second time, it's even faster because now it's compiled the code. Okay, so this is much, much, much nicer. And it still gives me the correct matrices, I hope. Let's try for 2. Yeah, looks about right. Ah yeah, and this matrix, I actually understand it, right? So this is the sigma z matrix on the first spin. Right, so now you have your Hilbert space ordering was down, down. So you have the -1 because the first one is down. Then you get a -1 spin up. First one is still down. And then you flip the first one up, and then it's +1. Right, so this is the sigma z matrix for the big system. But now I can do it for 10 qubits, no problem. Okay, good. So with this, I wanted to actually, we solved our step 1. Okay, so our next step is just to construct the Hamiltonian. Right, so I want to have this transverse Ising model. So I have this coupling matrix Jij, and I have this transverse field. And as I mentioned, what we want to do is we want to simulate these long-range Ising models. So I want to have in particular a coupling matrix that was implemented in this experiment. And what they did is, in generally, they had a coupling that decays as a function of the distance between these spins. Right, so here I have this index I of the spin. The distance would be I minus j, and then I take the modulus of this to some power alpha. And this alpha is the power law on how quick your interactions are going to decay. Right? If I make this alpha very, very large, then only the two nearest neighbors are going to be talk to each other, and then the longer range one not. If I make this alpha small, then I get longer and longer and longer ranged terms. And these ion trap setup, they were in regimes where this alpha can be more or less 1. So this is kind of an interesting regime, because then you go from an extreme long-range regime to a short-range regime in 1 dimension. Okay, so much just about the motivation. But at the same time, now we can just write a function that creates this Hamiltonian. Right? We have everything we need. Let's get rid of this bad function. And let's just keep this one. So actually, this one we also don't need anymore. But okay, let's keep it. It was fun. So this is the only function that we need now that creates all of the spin operators that I need to construct my Hamiltonian. So now what I want is I want to have a function that actually builds the Hamiltonian. So let's it called build, how did I call that? Oh, actually, wait, let's actually, yeah, no, let's just call it build Hamiltonian. Okay, and so what do I need for this function? Well, let's go back. We have, what are the parameters? We have J, which is the general overall interaction strength. We don't really need this because we're going to set it to 1 anyway. Remember when I said that you should always define one quantity as 1 and then define your time units in this energy? So we're going to do this with J, but let's just still keep it. Why not? The other thing we have is this exponent here, alpha. That's the second argument of this function. And then the transverse field strength, Hx, right, Hx. Okay, and we need our spin operators that we computed before, so that's fine. Okay, so how are we going to build this? Let's look at the thing again. We have this sum here, where we have to sum really over all of the i's and all of the j's. Right, so this is going to be technically a double sum, so I have to sum over all of the i's. And then I'm going to have to sum over all of the j's. Right, so I need my index j. But here, I don't want to double count. Right, so these terms are all pairwise terms. So you have all of these spins, and you have all of the pairs of the spins. But I don't want to have the term 2, 1, and 1, 2 in the sum. That's why I have the sum. The j is always larger than the I. I could always also double count them, and then I could write a factor of 1/2 in front of the Hamiltonian. But clearly, computationally more efficient if we instead now start with numbers larger than I. So I go here from I plus 1 to n only. And this is going to be my double sum. Right, so this is what I do. I loop over both of the indices and only over the indices where the j is larger than I. Okay, so what do we want to produce? We want to produce a Hamiltonian, which in this way we can start with like a matrices of zeros here, which should have the Hilbert space dimension dd. Right, so I don't have my Hilbert space dimension yet. So how do I do it? So well, I get my n, for example, from the length of this vector of the s-axis. This is going to be the number of spins. My function knows what this is. And then my d is going to be 2 to the power n, right? So I start here with this zeros function, which just creates a d by d matrix. And actually, by default, it's going to be a real matrix. Right? If I want a complex matrix in Julia, I would need to write complex something here. But actually, my Hamiltonian is going to be real. I only have sigma x and sigma z. There's not going to be any sigma y, so I can keep it like this, so this should be fine. Okay, how do I want to build this Hamiltonian? Let's first start with this transverse field part here. Right, so here I want to add to the Hamiltonian a transverse field in the spin I. So let's call it hx point wise I. Okay, so here, if I forget about the second sum, this is just the first sum. And for every spin I have, I'm just going to add one of these big sigma x matrices multiplied with the field. Right, so here I write pointwise multiplication, which means that really you multiply this number hx to each of the elements. It would also work if I do it like this, but I like this because it's a bit cleaner to understand what's going on. Okay, and then the second part here is now I want to have this second term here. So I have this matrix Jij. Jij is this matrix element j divided by the distance between I and j. Right, so what I want to do is I want to do the distance I minus jj to the power of some minus alpha multiplied with j. Right, so this is just really the prefactor that fully goes in front of the Hamiltonian term. And then I just multiply this by the set matrix for I. I just said here I want to be more clean, so this is a pointwise multiplication. And here I do the one with the index jj. And then this whole term I add to my Hamiltonian. Right, so if you're not familiar with this, if I write this is something, right, this explicitly means h equals h plus this. Right, this is just always a shorthand notation to add to something. Okay, and that's it. That's going to give us the Hamiltonian. Right, so really just a one-by-one thing from this formula here. So let's try it out. This is usually when you find out what mistakes you just made. So we still are with, yes, we still have this x operators for our n equals 10 system. And the set operators too. They're also for my thing system, so now I can build the Hamiltonian. Okay, and let's just do it for j. The first element was, let me put it a bit to the side. You can still see here. The first element of this function was j, the second one was alpha, let's say 3. Why not? Let's say a field 0.5. And then I give it the operators that I already computed, and this should be a Hamiltonian, and it's not. Yes, and I see what's going on here. Maybe I should do this. Oh, it doesn't like the negative. Why? Okay. Well, okay, let's just do it with division. Why not? Yes, exactly. But I think that the positive it also doesn't. No, let's see. It likes positive, but not integer. Then it says catastrophe. Cannot do it. No, it's true because right. This is also nice because okay, maybe not so nice, but this is a difference if you program in a more bottom language like C or so. In C, you would have to worry about all of these data types, right? You take integer to a positive power, it works. Only integer, it's going to give you an integer that comes out. But if you do it to a negative power, you turn an integer into a floating point number, and one has to be careful that this is not possible here. So, but here it's nice because this calculation of this thing here, it's only going to use integers in the memory, right? It uses less space because it only uses integers. Only at this point here, it's going to turn it into a double. And it does it automatically for you, except for it gives you kind of cryptic error messages that may be confusing. Okay, so let's stare a bit. This is Hamiltonian. It's nice because it has a lot of diagonal terms, which makes sense. These are all of the SZ terms that you're going to get. They should be all on the diagonal. And then I have a few off diagonals, which are here all 0.5, which is because I put my field to 0.5. So this is going to be the transverse field parts. So these are all the off diagonal SX elements that I get. Okay, good. So almost running out of time, but I mean, we are pretty much finished. So the last step that we really want to do is now to really, I'm not going to finish fully. I was lying in the 45 minutes. Okay, so the last part, right, we just want to really do the simulation of the dynamics for this. So this is the last thing that I want to do, and then I want to just very quickly show you that it works, and next time I will start playing with this function a bit. So this is now at the point where we can write the function that does the full simulation of the thing. So let's write a general function that does the, let's call it transverse easing model simulation. And this is now really the full function. Let's say I want to do it for n spins. I want to have my j, I want to have my alpha, I want to have my transverse field, and then the other last thing I want to tell it. Now, what I showed you all about exact diagonalization, it means building a time evolution operator and then evolving your system. Right? But fundamentally, you want to, of course, look at the time evolution step by step. Right? So we want to output things at certain times. So what I'm going to introduce is I'm going to introduce a time step here that I want to have my evaluation on, and the number of steps that I want to use. But it's important thing here is I just introduced this time stepping, but I would not really need to do it that way. Right? Because there's no approximation in this making small time steps. If, as was the question before, go to now time-dependent Hamiltonians, then, or what we see tomorrow, then the time step can be a convergence parameter to use. But here it's just for now purely convenience because it's just the time at which I want to plot my results. Okay, so in this function, I just want to put everything together before. We want to define some spin system with a spin lowering operator. I want to get my spin operators, many-body now. These are the big ones from this function with the built spin operators, which was the function that just takes this as m, and it takes this n, right? So this is going to be the build one. And then the last step that we did was building the Hamiltonian for my parameters, which was the order j, alpha, hx, using our spin operator. Okay, so this is just all what we did so far. Right, we have a function that creates spin operators, then we have a function that creates the Hamiltonian. So now we have to do time evolution. Okay, so what's the initial, let me also write some comments to make things nicer. What's the initial state? Right, so the state vector in general is going to be now a complex vector. So let's start with a complex matrix that's all zeros, which is as dimension d. So this will create the vector of the, wait, I don't have d here, let's just do n. This is my Hilbert space vector, and now of course I want to flip the spin in the center of the system. Right, so the motivation was to do this. Right, so I have a spin in the middle of this thing. So how do I do this? In a very simple way. I can apply a SX operator to it, right? So I can start with my initial state where I say the first element is 0, right? So this is the all down state, as we have found out. And now what I can do is I can define the state by in the center of the system. Let's, for example, do, right? So I can do this, right? So this is an integer division, right? This is also something that we've seen before. You have an integer, you divide. This is Julia turns it into actually a floating point. But if I write like this, I can keep integers. I just introduce some little fun things to do. And I can apply this to psi, right? And this is now applying sigma x to some spin in the middle. So this is going to give me the state which is flipped in the middle. Okay, then we have learned we need a time evolution operator. And we're going to do the lazy thing. So we're just going to do u, which is the exponential of minus imaginary times dt, which is my time step that I use. And then pointwise with the Hamiltonian. Okay, now I can do my loop to compute stuff. Okay, and this is what's doing it, right? So you see what I did here, because usually if I want to go to an arbitrary time, I would just put the time here, and this would be my time evolution operator. But I want to to plot things at certain times. So instead, I define a little time evolution operator just for a time step. And in every step here, it multiplies the time evolution to the next time. Right? So this is going to give me really vector after vector with these times. And then just to give you some output here, we're not going to evaluate any observable yet. We're going to do this next time. But here, so for example, just to make something nice, I want to have some output in the terminal. So I want to see, for example, I am in time step TT of steps. And then one advice is something that's always good to check is, I mean, this is the basic, is to check that the norm of your state stays 1. So here I use some very shorthand notation in Julia. If you want to output something in a string, one can use this $sign operator, and then this just puts this thing directly into the string. Trust me. Okay, and that's all what we need and how far we're going to go today. So now I can just check if I do something here. Okay, and now I had this function. This was transfer easing simulation. And let's say I want to do it for 2 spins first. I want to do it for j, for alpha something 0.5 field. And now let's say I want to do a time step 0.1 and I want to do 100 steps. Okay, and now the first time, again, it always takes very long. You see now you get all of the evolution over the time steps, and the nice thing you see here is norm, and the norm again stays 1, up to some uncertainty, which is 10 to the minus 14, 10 to the minus 15, which is just, again, this numerical imprecision. Right? So you see something like this. This is really equivalent to 1 within my double precision that I had introduced in the beginning. Okay, now the first argument here was the number of spins that I use. So now I do this for 10 spins. So still very fast, right? So at one point, this is going to get slow. Okay, this is already killing my computer. It's an exponential growth. Okay, it's hung up. All right, so this is it for today. So I hope I showed you that. Let me go back to the slides and actually do a little summary of this. I will finish this plotting for the next time. So just want to do a little recap of what I did. So I started today in a purely theory sense, just showing you how to really write down numbers on computers. Yeah. Yes, I can do this. But I really encourage you to just do it yourself. I mean, there's so much code online, so many toolboxes. If you really want to just do simulations, one can use those. But this is really doing it that really helps you to understand the structure. And the slides, the PDF slides, I share too. Okay, so I was showing you just how to write down numbers in computers and vectors in computers. I touched a bit about just diagonalization, and that diagonalization really solves a problem for you, because with diagonalization, you can then do an arbitrary time evolution. And the example that we looked at was this kind of initial spin-flipped state of this transverse easing model evolving as a function of time. And one thing I want to highlight, and this is where I will pick up next time, we saw that we have these gigantic matrices with a lot of zeros, right? So this is kind of inefficient. So next time I want to just do everything with sparse matrices, and you will see everything is much, much better. But it needs a bit of theory in order to do evolution with sparse matrices. Okay, that's it. Sorry, 3 minutes too long.